Evet arkadaşlar, öncelikle geçen haftaki konumuzu hatırlatalım. Hatırlarsanız çarpma ve bölme işlemiştik. Multiplication, I-multiplication, division ve I-division instruction'larını görmüştük. İşaretli işaretsiz sayıların çarpması, işaretli işaretsiz sayıların bölünmesini işlemiştik. İşte çarpma işleminin algoritması demiştik. Operandın boyutuna göre ya bu şekil ya da bu şekil oluyordu hatırlarsanız. Ya AL çarpılıyordu ya AX çarpılıyordu operantla. Bölme işleminde operandın size'ına göre ya AX bölünüyordu ya DX AX bölünüyordu. Operandımız byte ise AX'i bölüyordu, word ise DX AX'i bölüyordu. Sonucun yazıldığı yer byte ise AL, kalan AH. Sonucun yazıldığı yer word ise AX, kalan DX'ti. Bu komutların bir de I versiyonları vardı. I versiyonları signed, işaretli değerleri kale alarak işlem yapıyordu. Doğru işlem yapabilmek için eğer böldüğünüz ya da çarptığınız sayı eksili bir işaret ya da signed bir değerse, eksili olmasa da signed bir işlem value tutuyorsa I multiplication ya da I division kullanmalıydık. Geçen haftamızın örneği buydu. Bu hafta interrupt kavramını göreceğiz. Tek bir tane interrupt göreceğiz. O da teletype output dediğimiz ekrana çıktı alma diyebiliriz sizin tabirinizle. Onu göreceğiz. Lea load effective address diye bir instruction'ımız var. Bunun ne işe yaradığını göreceğiz. Kullanacağız. Bir de değişken kavramı ortaya çıkacak. Sizlere değişken diye bir şey yok demiştik o zamana kadar. Bildiğiniz manada int a eşittir 3 şeklinde C'de tanımladığınız manada bir değişken yok. Burada farklı bir şekilde bir değişken var. Onu göreceğiz. Evet, bu 8 kişiyle işleyeceğiz bu ders, anlaşıldı. Okay my friends, let me switch into English and start from the variables. In 8086 assembler, in 8086 architecture, we have variables. But this variable is only a memory location. It's important. It's just a memory location, not like these registers. These are not variables, these are registers. We create a variable from memory location. For a programmer, it is much easier to have some value be kept in variable named variable 1 or a bus than at the address, some physical address, especially when you have 10 or more variable. Compiler or 8086 architecture supports two types of variable. One of them is byte type of, the other is word type of. Syntax is very clear. We have define variable keywords with db and define variable word dv. Define byte and define word. You can memorize it that way. Stays for define byte, stays for define word. Okay. Now the instruction name is at variable name is at the beginning of the. Let me give an example from here. For example, variable name. I'm creating an Abbas variable with the define byte. The value is, for example, 73H. Okay, this is defining a variable. I can also create another variable with the word in it, and I can store another value in it. For example, I want to create some codes, nothing special, just some codes. Etc. There is one key important thing in here. If you want to define a variable, it shouldn't be run by the compiler. It should be after the return or after the return the operating system interrupt, or within, for example, we write some jumps that is not run anywhere. Let me write it. That will be more clear. Remember, this is unconditional jump. Jump somewhere is here, and within this jump, I'm creating a new variable. Define byte with a character of A. Okay, when I emulate this code to somewhere. When I emulate this code, none of these variable definitions will be instructed by this yellow line. If I look at the yellow line, none of this variable is instructed. This is important because this is some value put into memory. If it is instructed, it tries to resolve if it is an instruction or not. So it complicates the compiler. Let me show you an example with move AX command. For example, this is move AX command, B80100. If I create the new variable with, for example, define byte B8 age at the beginning of this code. This variable is stored in here, and after that, the instruction come after that, and this looks like an instruction, and the compiler confused. That's why it is important we create variables after return at the end of the program, or within, how can I say, not accessible part of program. Okay. For this case, I'm deleting here and looking at the example of this. Okay, I emulate this one. This is the move AX instruction, 3 line. The next instruction, increment AX instruction, is 1 line. Add CX AX instruction is 2 line. And after that, program is finished. This is the return line. After return, memory, look at the memory. Memory is filled with some value. This value is our variable value. For example, it puts the Abbas variable into, let me look at in here, into 1007. The physical address of 1007. The value is 73. And Elmas variable in 1008 and 1009 because it is word. Okay. Now, please remember the location of these variables. 1007, 1008, and 1009. And I want to add another instruction. Let me increase CX1. And I want to emulate. Okay. Now the memory location is changed. It is in 1008 address. 73 and 1173 is in 1009 and 1010. Okay, so we don't know the location of these variables by looking at this code. Okay, we can, by the way, create variable this way. Let me see some examples from here. By the way, name can be any letter or digit combination, but it must start with a letter. Value can be any numeric value in any supported numbering system, hexadecimal, binary, decimal, or symbol for values that are not initialized. Okay. As you probably know from part 2 of this try to move instruction is used to copy value from source to destination. Let's see another example. For example, it used variable in emulator. Let me paste it in here. Get rid of this or comment. It used variable 1. Variable 1 is 7. It is in 1008 address. Put it into AL, and variable 2 in 1009 and put it into BX. As you can see, you can use this variable like this. Okay. You can understand the locations after emulation. Please look at here. I'm going to zoom in here. Although it's stating that this is variable 1, the machine understands it as a 1008 because this is in 8 location. Variable 2 is in the 1009, it is in 9 location. 9 means data segment plus 9. Segment is now 100. Code segment and data segment, these are all 100. So it gets 1008, 1009. If I click in here, it shows the value stored in 1008, for example. Okay. Offset DS register. When confirmation was placed, offset by default load into DS register. When conf files load to register the same as code segment. First is offset. Blah blah blah. Var1, var2, word is 2 bytes. Okay. It gives an example of an error. For example, here is a program. It only defines variable. There is no instruction. So this happens. This gives some error because there's assembler has no idea about where the data starts. Okay. Compiler just converts the program source code to set of bytes. This is important. As you may guess, the compiler just converts the variable into set of bytes. This is called machine code. As we have previously said that this part of the emulator is machine code part, machine resolution, machine language actually. Processor understands the machine code and executes this, gets rid of this org usage nonsense. Okay, machine code, etc. Okay. Now I want to show you some other tricks for defining variables. You can put other value by using comma. For example, I'm going to put 1, comma, 5, comma, 0. When I emulate this in here, it put these values byte by byte because I use define byte and put 7150 consequently. Okay, this is important. You can put any amount of value by using comma. Also define word. For example, I'm going to use ABH and CCCH, for example. And I'm going to emulate this. When I click into this location, 1, 2, 3, 4, AB00, the lower part is written in first, the upper part is written and then later. CCCC, you can add how much info you want at the end of this variable definition. Okay, by the way, we can put decimal values, binary values. For example, we can use 1111B in here. And we'll look at the 1111, it is F in here. You can use binary, hexadecimal. For example, let's say this is hexadecimal. Let's put 17H in here. And also character. We can use ASCII also. I'm going to put A at the end of this variable. Okay, we have 17, 1, 5, 0, F with binary, and A with ASCII. It converts ASCII character into decimal or hexadecimal and decimal, and act as a number. Okay, you can use ASCII characters also. That's why, for example, I create the variable name Abbas. I define it as a byte, store the every element byte by byte, and I open a parenthesis and write my name. Okay, when I click in here, as you can see, it stores every character into memory byte by byte. A, B, B, A, S. This is space. It's also another character. It is also stored in here. E, L, M, A, S. And after that, the memory is 9999 goes like that. Okay, what if I change this into define word? When I convert it into define word, it is not going to be separated A0, B0, B0 because we concatenate them as a single value and write it out that way. But if I write it like this, I don't want to write the rest of it. Okay, when I click in here, as you can see, A0, B0, B0. This is word by word. But if I concatenate the string, the characters, it will not going to be separated. It is important. Okay, so we learned the variable definition and use of this variable. For example, we copy the value from that value to memory. This is the resolution of register memory combination. This is memory, this is register. So be careful. Instructions, let me open the instructions. For example, move instructions. Where's the move instruction? We know that these combinations are possible. You can use variables as memory in here. That's why we can use, for example, we can update variable 1 with bx in here. But it says, okay, variable 1 is byte type variable, so you can't put word type variable in it. That's why I'm going to change this into word for now. Okay, but in here we have variable 1 which has lots of value in it, but we are trying to put it into AX. What will going to happen? As you can see, it only gets the first 16-bit and put it into AX as an hexadecimal. And variable 2, which is 1, 2, 3, 4, put it into BX. Now I'm going to put BX, which is 1, 2, 3, 4, into variable 1. Where is the variable 1 location? Variable 1 location is here. I'm going to use update variable 1 with 1, 2, 3, 4. Okay, the only first elements updated, the rest of it stays the same. So this variable definition is only a pointer to memory location, starting of that memory location, and we know that we are looking for byte by byte or word by word. Okay, be careful, you can fill the memory with like this, but you can't use all of them. This is just filling the memory with some value, but if you call a variable, it only gets the first word or byte. It is important. Okay, for example, there is no memory in here. Let's see if it gives error or not. Yes, it gives error because there is no memory to memory move instruction. Okay, this is variables. From now on, you can use variables, but be careful, it should be after the return. Okay, we covered the variables. Getting the address of a variable. Okay, this is important. This is the instruction that we are going to cover today. LEA, L-E-A, load effective address. Please remember, when I insert some code in here, the memory location of these variables are keep changing. For example, I'm going to increase bx and look at the variable 1 starting point. It is 1009. I'm going to increase AX, add another instruction, and this time variable 1 will be in not 1009 but in 1000A. Okay, so we don't know where these variables are, but we have an helper which is LEA, load effective address. There is load effective address instruction and blah blah can be used to get offset address of this variable. We can get the offset of this variable. Please keep in mind that I'm going to delete this first. Please keep in mind that when we click on this memory location, it is in physical address on 1000A, but this 1000 part is 1000 parts comes from the segment. Which segment? Data segment. It is 100. We put 0 at the end of the segment. It is 1000. And we add the offset. The right part of this address resolution, the right part of this address is offset. This is important. And it's saying that it will get the offset address. If I use LEA for the variable 1, it will get A for me. Not 1000A, but just A. Okay, let's use LEA. How can LEA be used? I'm going to open instruction set and go to LEA command. LEA works like that. register memory. There's only a single use case. You can't use any other things. I'm going to load into, let me say, dx, the address of variable 1. I'm trying to resolve the address of variable 1 into dx. Okay. Let me show you the address of the variable 1. It is 1000d. I can clearly see it in here. The address of variable 1 starts from 1000d. This LEA instruction, load effective address instruction, will load the d into dx. Okay, some code is run. The LEA resolve the memory location of this address part, starting point is address part. The D location, D address will be stored into DX, because we tell emulator that resolve this memory location to us and give us the offset into DX. We can change this into AX, BX, CX, DX, or for example, let's say this can be byte. I want to resolve this into AL. But if I change this into, what is the error? Variable 1 define byte. Yep. We are trying to resolve the offset of variable 1. Yep. What is the error? Variable 1 into, let's say, h. Wrong parameters. Register memory. Do we have to use 16-bit? That indicating address of can be a reminder. In order to tell compiler that data type address should be used, byte better, work better, blah blah. LEA is always used with BX. Oh, because the address location can be higher than 8-bit and it must be 16-bit register always. The location of, for example, when we go at the end of this location, the address of offset of this part is here. The offset is bigger than 8-bit, so it is not accepting 8-bit register. I also learned that. Okay. Okay. There are some other use cases. For example, we can put bx into parentheses, remember. And for example, we have echo keyword. Let's say the capital letter. No, there is no capital. AB73 is equal to 1000 H, and I put AB73 before this parenthesis, and I want to resolve the address of this location. Here's the exam question for you. We have this example. What will be the AX value after this program run? What is going to happen? Variable 2 location. Variable 2 will be 1, 2, 3, 4. Bx. Bx will be incremented. It will become 1, 2, 3, 5. Okay, we have 1, 2, 3, 5 in here, 1000 in here, 2000, 2, 2, 3, 5 will be the address of this AX. Let's see. Okay, variable 2 load into BX, incremented 1, 2, 3, 5. Okay, we have constant value, which is AB73. Load this effective address into, for example, it calculated in here. Machine language is in here. 1000 comes from the AB73. BX comes from the BX. It's going to resolve the location, which is 2 to 35. We calculated correctly. Okay, so the load effective address works for like this. Check the value, get address, modify the content, check the value, blah blah. You can look at these examples in your tutorial. Please note that only this register can be used inside brackets. You already know this. We can only use this variable within the parentheses, within the not what is this parenthesis? It's brackets. Yeah. Square brackets. Yeah. Constant, it's equal, etc. Okay. We learned the load effective address. We learned the variables. Now the easy part, the interrupt part, the easy and fun part. Okay, let's go over here and open the interrupts. Yep, here's an interrupts. You can read all of these instructions, but the easy part of interrupts, it only gets an immediate byte value. You can't use greater than 255, which is maximum FF. You have to put simple instruction, immediate value, which is 8-bit. Okay, let me copy this example from the PDF. Okay. Okay, let's say AL has a value of A in it, or 41 hexadecimal in it. In order to call teletype output interrupt, we need to put 0E into AH before calling interrupt. If AH has the value of 0A, E, and I call interrupt 10H, this means the resolution of this combination means teletype output. So what I am telling you. If I open the interrupts, as you can see, there are lots of interrupts. But as you also can see, there are lots of same interrupts. This is 10, 10, 10, 10, 10 goes like this. For example, 21, 21, 21 goes like this. But the combination is with some other values. For example, the E. We put E into AH, and this becomes teletype output. Let's say A. If we put A into AH, write character only at cursor position. This is an interrupt for writing character only at cursor position. Something different in interrupt. Let me go to 13. This means write string interrupt. The AH is always the second part of these interrupt combinations. For example, this. If AH is 2, it means read these sectors into memory. If AH is 3, write these sectors. Okay? So, in this microprocessor lab lesson course, we are going to only cover a single interrupt, which is teletype output. As you can understand, it's just a printf. Okay, let's emulate this code. We put 41 into AL. Okay, Where is 41? Oh, we put it in AL. Okay. 41 means A in hexadecimal. Please look at here. This is hexadecimal. This is decimal. This is hexadecimal. Okay. How you are going to know that the hexadecimal ASCII version of hexadecimal? We have ASCII table. You can just Google it. Open some link. These are predefined constant table defined into every architecture of computer. So we know that, for example, 41 in hexadecimal, 41 in hexadecimal is capital A. In here, 41 in hexadecimal is capital A. For example, lowercase a. Lowercase a is 61. So there is 20H difference, or how many? 22, 32 difference within decimal. So if I add 32 into capital A, it becomes lower a. Okay, I'm emulating this one. As you can see, it just print out an A to the screen. This is emulator screen. And I'm going to change the value in AL by adding 32 into AL and call interrupt 10H again. Okay, the first interrupt, print out the capital A, and we add 32 into AL. AL becomes 61. These are hexadecimal. 61 interrupt 10 will be called, and the lowercase a is written into screen, as you can see in here. Okay, let me close this example. This is calling interrupts. You don't have to put E into AH again and again, because we didn't change AH, but for example, within this memory, let's say I'm going to use X as like this. You can't call interrupt 10 in here because AH has FF in it, so it will do something else for the next interrupt. I don't know what it's going to do. Let's see. Is not supported. There is no interrupt with combination of 10 and FF. Let's go over and look at the combinations. There is no 10 and FF combination, so it says not supported. So in this case like this, you have to be sure and put E into AH again, so that we know that it will print out some value. But this time we update AX with FF. AX is FF. We are going to add 32 into AL. AL becomes 1F. I don't know what 1F is. And we put E into AH so that we can print out AL. When we print out this value to the screen, it didn't print out anything because 1F doesn't has a value in 1. There's no 1F in hexadecimal. Hexadecimal value finished at the 7F. But 1F can be here. Where's 1F? 1F. 1F, yeah, there is 1F, but it is unit separator. I don't know what it is. So let's change the 32 into something 32, 33, 34, 34. Let's say at 34. Okay, some values. We print out the capital A. We put on E. The value of AL is 21. 21 in hexadecimal ASCII table means exclamation mark. Okay, now it will print out exclamation mark. Yep. So be careful. We do want to print out the lowercase version of A, but we updated the AX. That's why we can't print out lowercase a, but exclamation mark. Okay, so that's it. The topic is covered in here. Now we have examples. Before diving into examples, I want to see if there is any question. Any question about anything? This topic is a bit different. Seems like there's no question. Okay. Let me close this interrupts ASCII tables. For example, look at this interrupt. Interrupt 21 bit 4C. If AH has the 4C value and 21 interrupt comes, this means the correct version of return control to operating system. It stops the program. We should write not return, but this. Let me copy this in here, but I can't write it like this. It should be like this. Okay, this is the correct version of return. Can arithmetic operations be applied on variables? Let's try. Okay, let's say I'm going to use red and we have variable 1. Let's say this is byte. Let's say put it into 5. Some ask that if arithmetic operation like increase can be done with variable 1. This is a simple implementation of this question. When I emulate this one, location of variable is in here, 1005. I'm going to increase that and 1005 is increased. How can you understand without writing a simple example code? As I said earlier, this is a memory location. If your instruction, for example, increase, we try increase. If your instruction supports memory, you can use variable. If your instruction does not support memory, is there any instruction like that? If your instruction does not support memory, you can't use variables. As long as it supports memory, you can use variables because variable is actually memory. Any other question? So I'm diving into examples. Okay, first program. Write a program that writes your name to the screen. You must use a DB variable. Okay, let's print out our name. Let's say we have a name variable which is defined as DB. We can concatenate, combine all of these, and we want to print out the value. In order to print out value, we need to put 0E into AH and By the way, I forgot to mention that, but interrupt 10 only print out the AL value. It print out AL, nothing different than other things. It just print out AL. So we need to put the value into AL. We put name variable into AL. And after that we call 10H. Oops, it doesn't like that. Define bytes. Oh, we see this error. I want to test something. No zero prefix. Name db a or wrong addressing or undefined var name name. Do we have to use AX? Oh, of course, we can't directly use the resolve variable like that. But let me open the variable part. There's no error in here. Yes, there's no error in here. Get rid of it. Why it gives an error on my name? Why? What's the difference? Oh, it doesn't accept ASCII this way. Let me write 61. Hexadecimal. Something seriously wrong in here. It accepts 7. Not accepting anymore. Now accepts. What changes? It didn't like the variable name of name. Or yeah, it didn't like the name. Maybe it's predefined value. Let's say my name. Yeah. So we learned that we can't use name keywords. Okay. This is a bit confusing for you, I know. Okay, I put it into AL. I'm going to use interrupt 10H with E combination. This will print out the variable, and let's see the output. Okay, it will only output a single character. Remember, it will only print out the AL, and AL didn't change in anywhere. So this is not the whole variable. We only store the starting point of this variable. Starting point is 1008. So it prints out the byte version, which is a single character in here, A into screen. So how do we going to print out every keyword? Should I call again and again so that I can print out every character? No, the AL isn't updated, so it just prints out the AL value, which is A, goes like that. So before calling again, I need to increase the location of this. That's why I'm going to use load effective address into bx. Okay, it will find the location of my name, and I'm going to use bx in here. After that, I'm going to, before calling interrupts again, I'm going to increment bx by 1, that I can move into memory. Okay, bx's result, it is 10. Let's go over and look at the 1010. Yes, my name starts from 1010 hexadecimal. Okay, now this resolution, this address resolution is 10 plus data segment, so that it will put into a character into AL, we put E into AH, and call interrupt 10 so that a character is printed out. Now that bx is increased by 1, it will become 11. The 11th location, which is, let's go over and look at the 11th location, is 62, the lowercase letter of B. It will print out B. Oops, it didn't print out B. Why? Because we still didn't update the AL. So I need to update AL with BX value before calling interrupt. Okay, we print out A, increment BX, update the AL. AL is updated with 62. Now it print out B and update the BX and update the AL. Now it print out the second B and end. But my name is longer than ABB, so what am I going to do? I need to run this code in some constant value of some conditional jump. Sorry for my notification sound. I'm going to delete this part. Okay, I'm also delete this one too. I'm creating a loop. Let me give a name. Remember, these loops runs cx times. How many characters do we have? 5, 5, and 1, 11. We have 11 characters. And I'm going to call interrupt 10h 11 times. But before calling interrupt 10h, I'm going to increment bx and update AL. Why I use bx in order to load location physical address of my name? Because I can put bx into square brackets. You can't use cx, dx, ax in square brackets. You can only use bx or bp or source index, etc. That's why I use bx. Okay, I updated it like that. This is going to write my name to the screen. Oh, it starts from B, writing out this at the end of S, it will overflow and print out something different. Yep. It will print out the this location also, because we start from the wrong location, because it should print out, then later increase. Maybe at the beginning of in here I should call 10h, and this will run 10 times. Yep, I can successfully print out my name. Okay, we can do this by constant times. We know that the loop keyword runs cx times, but we can also look for a conditional jump. For example, jump equals. At the end of this interrupt things, let me compare AL with something. Let's say 0. It will check if the 0 comes, 0 comes, 0 comes, 0 comes. So I'm going to insert 0 at the end of this memory location. And when the 0 comes, let's get rid of this CX. What was the GE looking for? GE is looking for 0 flag is 1. So the result is 0. Okay. It will compare AL with 0. If it is 0, it will jump. No, it shouldn't jump. The opposite version of GA. We need jump not equal. Okay. So this is the conditional version of printing out my name. Okay, now I'm going to change this variable because I have a first name. This will print out my whole name until the 0 comes. But if you have a 0 in your name, ASCII table, in ASCII table, I don't know if 0 is 0. Let me check. Yes, 0 is 0. No, 0 is not 0. 0 is number, 0 is 30. So it will not give an error. So no problem. But for example, if you choose S, for example, let's use smaller letters. If you choose S to stop, you can't put S like this. You have to use this. Okay. If you use it like this, oops, it didn't stop. Why? Why it didn't stop at the beginning of this session? Because we keep comparing it with 0, but we should compare it with S. It will only print out Abbas, not continue. So be careful, you have to choose a value that is not in your name. Okay, this is first question. Okay, second question. Write a program that writes your name to the screen backwards. You must use a DB variable. Okay. We have a name, my name. We want to write out this in backwards. We can do this in reverse order. For example, let me write we need to count the element size. We can just use a loop, not the conditional one, just a loop. Okay. How many times this should run? This should run 11 times. We shouldn't print out the first character. It should print out 11 times, but it should start from at the end. This is the 11th element. So I'm going to print out the 11th element and decrease bx. Yep, this should work. Not exactly, because we put 0 at the end. The location of my variable is, let me look at the location, it is 13. Bx is 13. Bx is 13. Where should we start? Maybe we start from 10. Yep, this is the correct version. So this is predefined variable. We predefined the size of a variable. For example, this will not going to write out my first name in here. To print out something different. That's why I'm going to get rid of this CX and use some conditional jump. Let me erase it. The condition is with compare option, but this time I put 0 at the beginning of my name. Okay, it will compare 0 with my AL. I need to update AL beforehand with something. Here we need to print out some character. This should be after updating AL. I put BX like this. No, we don't know the size of this variable. I need an offset. How many elements are there in here? How can I do that? Any idea? Yeah, name is the reserved word. We learned in a hard way. Interrupt Tenash prints only AL value. Thanks, Utku. Yep, only 8 bits because ASCII table can fit in an 8-bit. But how can we reverse this name without using constant? We can count. This is ugly, but we can count. Let me put 0 at the end again. And we have a counter variable. And for example, use CX as a counter. Starting from beginning of this DB, move EX make comparement with 0 if the last element is came or not. If it didn't come, it jump. But before that, I need to increase CX. Yep. So this is counter. By this way, I can count the number of characters. After that, I can use loop. Plus, I can't use CX in here. It's getting uglier. I can add only once. Add CX into BX so that I can only use BX, but I need to decrease BX after printing out. Yep, this is the ugly version of my reverse codes. What is the problem? It didn't put semicolon. Okay, it will. Oops. There is a problem. CX is 1. We address of my name into AL. We need to increase BX in here because we need to move forward. Increase BX at the end of in here, so we are in the correct location of BX, so we don't need to add CX. Okay. No, we are not in the correct location. What is the error? We get the BX, put it into AL, increment BX, BX goes by 1. We compare if the AL is 0 or not. If not 0, jump. CX is increased. Okay. Let's emulate one by one. A little delay would be helpful. CX is 9. CX is 10. My name is 11 character with the space. CX is B, 11. Okay, now it should finish. But why it didn't finish? Let me reload this one. AX73 for the CX is C. 73, 90. Oops. Okay, where's the error? We are trying to count. We are looking for the 0 value. We keep putting that value into AL and compare that AL with the 0. Jump not equal to. Jump not equal to means, let me go over and look at the jump not equal to. If 0 flag is 0, then jump. If 0 flag is 0, the substitution is 0, then it will jump and count. 1, 3, 4 goes like that. Let me reload again and goes one by one. BX is 1A. 1A means the name starts from here. We are 0 at the 30. Yep. 1A move 61. Put it into AL. Okay. Bx is increased by 1. Now Bx is 1B. Okay. We compare AL if it is 0 or not. It is not 0. 0 flag is 0, so that it will jump. Cx is increased. We get the value 62, which is B. Okay. Cx is increased. Another 62. And another 61. Okay. And now it comes 73. 73 is loaded. It is S. 73 is not 0. Okay. 73. 20. What is 20? 20 is space. Okay. Space is not 0. Okay. 65 is E. 6C is L. 60 is M. 61 is A. 73 is S. Now we are here. Oh. We put 0 character, not 0. Oof. Sorry for this. This is not. These are not the same things. This is null character 0. This is character 0. Hexadecimal version of 0 is 30. Hexadecimal version of null is 0. So I put 0, not 0. So this should print out my name. There's some offset mismatch. Okay, we count in here. Let me reload in here. Delay run. Look at the CX value. It should be B. Okay, we have B. We have increased CX one more time. Now this is wrong. CX is increased by 1. Before diving into here, we need to decrease CX by 1. Oops, why it didn't work? Decrease, not CX, decrease BX. Location of. We still didn't at the correct location. Why is that? We get the value increment BX, increment BX, increment BX. And we are at the 0. This 0 is written in there. Okay, let's change this code like this and emulate it. Yeah, it will print out my name, but put 0 at the end, because at the end we have 0. We can again decrease BX, but no need. Okay, this is the reverse version. Let's see the original solution. Original solution is here. Okay, what it has done, it updates data segment. It's already 100. It uses BX in order to resolve the variable name isim. It uses correct return statement, put E into AH, and use the combination of source index and base register BX. It counts counter. Within this counter, if the result is 0, it will jump to end. This is meaningless. You can directly use this one. Anyway, it counts within the source index and put it into cx. This will run cx times, and bx plus source index, it will decrease source index. But bx is showing the starting point. How this is going to name backwards? Bx address, yep. We didn't update bx in here. Bx plus source index, the last location. Source index is decreased. Okay. Okay. Another answer for the second question. Any question? Keşke mikrofonu açıp söyleseniz de beni boşuna uğraştırmazsanız arkadaşlar. Buraya yazdığınız şeyleri göremiyorum çünkü malum. Third question, third example. Let's see. Write a program that writes a given lowercase string variable to the screen with uppercase characters. Yani diyor ki şöyle verilmiş bir ismi bu hale getiren kodu yazın diyor. Write a program that finds lowercase and make them uppercase, capital letters. How you are going to do that? Remember, lowercase and uppercase has constant difference. The difference between 97 and 65 is 32. The difference between let me zoom again. The difference between B and B is 32 again. So the difference is constant, but you have to check if it is lowercase or not. So this program is a bit longer. Let's understand the algorithm. I will not write all of this program. I will give you some time for days and expect you to find this answer for yourself. It's already too long for this lab session. Okay, you have to check if the character lowercase. If it is lowercase, add 32 decimal to it. Not add 32 decimal and let's say print that character. If not, just print. That's it. This is the algorithm, but you need to check if it is lowercase or not. If it is lowercase, how do you check if it is lowercase or not? Within this ASCII table, if the value is between 97 and 172, it means it is lowercase. Or you can check if it is greater than, for example, 90 decimal, it is possible that it is lowercase. If it is smaller than 90, it means it is uppercase. We are not going to add, we are subtract. If it is lowercase, we are going to subtract 32. Okay. I want you to write this code on your own. This is your, let me say, a homework. I'm not going to give a grade or something, but try to write your own code, okay? I'm stopping this record in here. If there